Okay, recording started. Thank you everyone for joining today. We are glad to have Dan Russo as a speaker today. So Daniel Russo is an associate professor in the Decision, Risk and Operation Division at the Columbia Business School. He completed his undergrad in math and economics at University of Michigan, and then his doctoral studies at Stanford University under the supervision of Benjamin Van Roy. After that, he worked as a postdoc at Microsoft Research in New England, and he won several prestigious prizes. And yes, we are very happy to have you talking today about theoretical interpretation of what people do in practice. I'm really looking forward to your talk. Thanks a lot for accepting our invitation, and the stage is yours. Thank you again.
Okay, thank you so much. Yeah, I'm excited to be back in the RL theory seminar. I think I gave this seminar, one of the first ones ever in back in COVID, back in 2020, and I think it's been a great initiative throughout that whole time. Okay, so I'm going to talk about some new work. It's going to appear at ICML. So if you're going, you can also catch me in person, at least briefly there, and we can chat about this stuff. All right, so before diving into the meat of the talk, I'll start with kind of one slide of very high level kind of framing and overview, right? And I think one thing that'll come out of this is my framing is gonna contrast a little bit with the use of RL to make LLMs better. It's gonna be framed a little bit in reverse, okay? So a question that's kind of been on my mind lately, framed very high level, is kind of comes from comparing these two paradigms. Right, so on the left, I have what I view as the main engine that has driven this era of AI development. Okay, and it's taking whatever problem you have, which generates rich data, framing that maybe as data sets that show you examples of collections or sequences of tokens, and then training a model to be able to imitate that distribution through sequence modeling. Okay, and there are many notable things about this paradigm. One is that the data is kind of passively collected. There's no notion of making decisions and influencing the environment and so on. And on the right, we have a paradigm that I've spent much of my adult life thinking about, one where we think about an agent that is interacting with the world. They are taking actions that have consequences that compound across time, and they are learning from the feedback gathered actively through their actions. Okay, and my feeling is that the paradigm on the right reflects a lot of what living actually is, and is sort of the right framing for thinking about a broad class of problems, but that the algorithms on the right are pretty finicky. We really don't know how to do a lot of things. And that on the left is what really is a more mature, developed engineering practice. Okay, and so from that, you might ask, what primitives in reinforcement learning can be recast as being just sequence modeling done carefully, sequence prediction done carefully. All right, and I've been thinking about this in different angles. One paper, which I won't talk about today, is thinking about the problem of exploration and epistemic uncertainty quantification as being just training and generating from sequence model, done carefully, right, on the right data and conditioning on the right stuff. And today's paper is going to be thinking about improving a policy by sequence prediction on the right filter data. All right. So with that, let's dive into the real framing of today's talk, and I'll spend a sequence of slides kind of giving broad build-up to the question we ask. All right, so let's dive in. I'm going to kind of overview the current pre-training to post-training paradigm for building models in my own lingo, so that everybody's kind of at least knows what I mean when I say things. Okay. So I'm going to think of the pre-training phase of building large generative model synonymously with imitation learning. Okay, and the idea is that a lot of the data we may be imitating reflects not just like laws of the physical universe or something, but actually human actions. Okay, so you want to learn to speak like human, well, you can imitate their language. Learn to code, well, you have all sorts of both hacky and professional quality code all over the internet. Okay, so you can learn to predict the next token in all of these domains. And then it's natural that in robotics, a way to make progress is to actually have people demonstrate the right way to perform certain tasks, do the same sort of thing. All right. Now, it's kind of obvious that some of the behaviors that you would get out of that process are not ones that you want to then turn around and use. Okay, so the post-training phase flips around the thinking to, instead of wanting to just imitate broadly the distribution of behaviors in the data, I want to at least be able to select the good ones, and I may want to be able to learn new behaviors that kind of combine the ones I've seen in a useful way. And all of that is a profound shift to viewing the generative model now as a policy for decision making for some task. Okay, this policy could be a chatbot that leads to fulfilling conversations. For math reasoning, it's usually kind of a simple deterministic environment where all the thinking happens in stages through your head. You see a prompt, that's kind of the state. You append your thinking to it, that's the new state. You append and you append until eventually you get an answer and you get rewarded on whether it's right or wrong. Okay. In robotics, it might be similar, except that you would likely have observations that are stochastic and resulting from the environment. Okay. Everyone okay with this idea? Okay. Now, broadly, once you accept this reframe, there's the natural question is, how do I make this policy better? Right? I could just generate new actions from the policy, but how do I make the generations good according to some measure? Right? And the version of this that I find most comfortable and natural, operations researcher, is explicit policy optimization. You write down exactly what your goal is for that optimization procedure. So you form some kind of an objective. Maybe it's something like maximize the probability of getting the math problem correct. And then I take explicit gradient steps, or I solve some kind of trust region problem, and then do that repeatedly so that I improve along that objective and explicit. All right. And this is nice and satisfying. What I'll consider to be sort of a downside of that is we took the engineering kind of stack that led to pre-training and all of those successes, and we turned it into PPO, which is not how I wanted to improve my language model personally. So there's a kind of a different idea that is sitting there, which is to continue doing imitation learning, but to imitate different data. Okay, And that imitated data could come from experts that you hire. You just think it's better data than on the internet. Or increasingly, it could come also from your own model. All right. So given you have a good model, you could generate trajectories, keep the ones that succeeded according to some measure. Okay, and this could be that they got the math problem right. It could be that an expert was paid to judge which ones were good or not as answers. And then you throw those into a batch of data and you do imitation learning on those. Continue to do imitation learning on those. Okay, and conceptually, I kind of like that this is just the same thing. The whole process is about tilting the data distribution, but nothing about the training seems to be different. There's no PPO. Okay, but it's kind of unclear what you're trying to accomplish. There's no explicit decision-making objective. And all right. So I'm going to be studying that thing on the left, the continued selective imitation. And once you start looking at it for a little while, you realize that the same idea is recurring across communities. Okay, so in addition to kind of LLM post-training, there's a idea that became popular in offline reinforcement learning post the advent of transformers, which is to, if you've heard of something like returned condition reinforcement learning or decision transformers, what those do is they try to do something like play an Atari game by having observed many ways of playing an Atari game and then trying to predict the action that was played conditioned on the game ending with a high score. It looks into the future because you've seen these games to completion. You can condition on the score being high and try to decode which action was taken. An odd idea. All right, but that ends up producing some impressive empirical results in a number of cases. Okay, and so because these are kind of the same operation, I'm going to pull them together and try to give them a name. And the name I come up with is success condition. All right, and all of them are doing the same principle. Learn to act as you would have, given that you eventually succeeded. Okay, so imitate whatever worked out. All right. So in some ways that feels natural. Copy what works, don't copy what doesn't work. But there's also something a little strange about this in that you're kind of peeking into the future. I mean, maybe whatever succeeds is luck. Okay, so you can kind of convince yourself different ways about whether this is a good idea intuitively. All right. Now let's see what's been said before, and more I think has been said in the offline RL space. Okay. So here's the abstract from the decision transformers paper. And I think it's just meant to be informal, but it says, unlike prior approaches to RL that simply fit value functions or compute policy gradients, decision transformer simply outputs the optimal action by leveraging a causally masked transformer. Okay, so you can kind of see the promise here. You get an offline data set, you do no RL, and you just return the optimum. Now, follow-up's going to call this into question, saying that, okay, this procedure of imitating whatever worked out does not yield the optimum. Okay, and can actually offer failure in the all right. So the main question asked in my paper is, if this procedure does not recover optimal policies, how do I think about what this is doing? Right, and what does it mean if it doesn't recover an optimum? Okay, so I'm gonna clarify that if you have these two paths to improving a policy, And people are often kind of going through path A and then later doing some of path B in practice now. I'm going to say that actually the divide between these is not as stark as it seems. Okay, so I'm going to say that selective imitation, path on the left, is actually explicit policy optimization in disguise. Okay, so if you can, it forms no objective and it computes no gradients, but it is exactly solving a trust region policy optimization problem to improve the policy as much as possible while staying close to the original policy. Okay, and it's exactly the sort of thing that is kind of obsessed about in path B. Just not written down. Does framing make sense? Questions here before we dive into the details?
I think all clear. Thanks.
Okay, thanks. All right. Okay, I copied some slides over twice, sorry. So let's go into formalizing what this is. All right, and if you think about many of the examples, considering they have this feature that you proceed in episodes. There's a math problem, and then there's a different math problem, and then there's a different math. Right? It doesn't just continue ad infinitum. All right, so what we're going to express this as a terminating Markov decision process. I'll denote a trajectory by tau. It's going to basically continue as state, action, state, action, state. And the first time you stop will be the time that you hit some terminating state. Okay. And I'll divide the terminating states into those that are successful and failed. All right. So basically what this means is to do success conditioning, you must have a way of looking at the trajectory and labeling it as a success or a failure. Okay, if that procedure does not exist, if there's no binary label of any kind, then somehow there's no notion of imitating the successes. Okay. And if there's time, I'll discuss at the end kind of what this paradigm means when there's no binary way of doing things and how people approach this. Okay, but for now, let's say that you end in success or failure, and R denotes the success failure flag. Okay. Also important notation here is I'll think of data that is coming from a behavior policy pi naught. This plays two roles. It's kind of the thing you want to improve, and it's also the thing the data is. Okay. Now, there's two definitions of what a success conditioned policy is. One is just Bayes' rule. You are going to play an action according to the probability that that is the action you would have picked in this state if the future ends in success. Okay, so it's literally the action distribution along trajectories that happen to end in success. Now, the way people actually implement this is they generate data under pi naught, so they should say E sub pi naught, and they train to predict actions as well as possible and cross entropy loss, having filtered out two trajectories that succeed. That's cool. Okay. So let me flag that language modeling is like something like those math examples are kind of a simple special case where the state is the sequence of tokens you've generated so far. The policy is a rule for generating the distribution of the next token given the state so far, so the previous ones. And the transition dynamics are deterministic. You just append. Okay. And in many of these examples, the state is really something like a history. Similar. Does that make sense? Okay. All right. So this is I often find it clarifying when seeing a method that's maybe actually being used and so on, to come up with a very dumb example where the method really doesn't help much, or it fails, or something like that. Okay, and so this is that kind of troubling example. It's going to set the boundaries of what we expect from this success conditioning operation. All right, and so here it goes. It's a very simple problem in which the episodes terminate after just one action. Okay, and it's a stateless problem reflecting a two-armed bandit. So there's two actions, action 1 and action 2. Both succeed with probability that's about 50%, but action 1 is a little worse than 50%, and action 2 is a little better than 50%. So clearly the optimal policy is just play action 2. That's what you would want to do if you knew. Okay. Now you start with a behavior policy though that is uniform. It's kind of purely exploratory. It plays each action with 50-50 chance. Okay. And you can ask what happens if I apply success conditioning. Do I kind of, as in the abstract of the decision transformers paper, do I lock into optimal actions or what do I get? Right. So what you find is that the new policy improves over the behavior policy, but does so very, very slightly. Okay. So given that you succeeded, it is slightly more likely that you picked action 2 than action 1, but just barely. Okay, so the new policy is going to tilt its probabilities very slightly toward action 2, but not a lot. Okay, and I'm teasing ahead here. This is really going to be the failure mode of this method. Sometimes you do success conditioning, and it doesn't change the policy much at all. It's not like it had disastrous distribution shift or failed by moving you towards some kind of very different and very bad policy. It just didn't move you much at all. Does this make sense? All right. So I think one thing that example sets the boundary of is that there is not going to be some kind of a, clearly I could make this example worse, right? I could, instead of 0.505, I could make it 0.5 plus epsilon, 0.5 minus epsilon. Make this example horrible. Okay, technically. So there's going to be no way of understanding this operator that is completely problem independent. And so there's going to be something about the problem and the behavior policy and so on that characterizes whether it's a good fit for the environment. And once you work through kind of the algebra, something pops out that really does characterize this. Right, and it happens to be pretty clean. So I gave it a new term, called it the action influence. All right, so what is this? It's the following term. So I'm going to call it the influence of the action draw at state S. And intuitively, you should think of this as trying to measure to what extent does the randomness in my action at this moment drive whether I ultimately succeed at the end of the episode. Okay, and if the randomness in my action right now bifurcates whether I kind of like divides whether I'm going to succeed or fail. If I get heads, then I always succeed. If I get tails, I never succeed. Then intuitively, it's going to be obvious how to do success condition. Once you condition on successes, you always behave a certain kind of way, and that always leads to success. Okay. But if there's kind of more noise, this operator is not going to be as effective. Okay, like in the failure mode example. Okay. So how do we measure this? It turns out this is the right way. There's a Q function, which is the usual object, but because rewards are binary, the Q function is just the probability that you succeed at the end of the episode, given the state you're in and the action you take. Okay with this? Now, the action influence is the coefficient of variation of that Q function with randomness over the action draw. Okay, so it's the standard deviation of the Q value over the action draw divided by the expected value of the Q value over the action draw, all squared. It's okay. All right. Now I have just like a hunch that is quite speculative that if you went through and saw the examples where post-training really, really works well, and you saw examples where post-training is not working very well, this term plays a pretty big role in defining this. But it's an unchecked hunch. Okay. So now with all that set up, I can kind of give you the main result that I've already flagged, but give it to you in precise math. So yeah, I think that I'm going to show you this kind of meaty looking theorem. It's helpful to have the superficial view also here. So there's a question in the chat.
Yeah. Basa, do you want to unmute? Or?
Hello. Yeah, I just wanted to ask a question about the bandit example. Do you hear me?
I do.
Yeah.
Oh, okay, nice. I was just wondering that it seems to me intuitively if you had kept updating the policy iteratively, like always clone your previous policy but weighted by the success, it should eventually converge to the optimal, right?
Yeah. So I do not prove that. I think that someone else has subsequently shown it. But you're right, definitely. In this example, you do continue to convert. If you do this repeatedly, you will converge to the optimal. I think that the reason, so in some ways though, that view is going to emerge from unpacking what this operator is. So I'm going to take that view of this procedure as a way of updating your policy, not of in one shot optimizing your policy. And for historical reference, the initial study of this kind of procedure came out of offline reinforcement learning, where the proposal was to do this operation once, not repeatedly.
Okay. Yeah, I was just wondering that. Oh, sorry, go ahead.
No, I think that's some of what leads to this kind of confusion, where the doing it once led to very good performance in a number of examples. And that led to other people like, wait, this doesn't work. In general, this does not give you a very good policy. And I'm trying to unpack what's going on with there.
Okay, yeah, thank you so much.
All right. So let's try to show that in a way. Let's try to think of, the bandit example is sort of tantalizing in that it looks, okay, not like an operation that takes in a behavior policy and returns the optimal policy, but as an operator that takes in the behavior policy and returns a new policy that is somehow better. It may be only a little bit better. We're not, we're going to have to see how much, but let's see if we can formalize that view. Okay. And so I'll show it to you in math. Here's kind of the very superficial view of the setup. Okay. What we've done so far is we've unified some popular methods like decision transformer kind of methods and SFT plus rejection sampling under a single name, success conditioning. And I'm combating this kind of pervasive view that this procedure is sidestepping RL, because RL is policy gradient and there was no policy gradient. Okay, there's no value function. It's kind of everything's implicit. And let's say that this is secretly solving an explicit trust region optimization problem. Okay. So it's really in that RL family. All right. So what does it mean? Let me write down a template of what a trust region optimization problem looks like. Okay, so there's this local policy improvement objective. So it looks like a policy iteration thing, Q function kind of thing, where you try to improve as much as possible over the behavior policy, like increase the advantages or the Q functions, subject to a constraint. Okay, and the constraint is that on average, over some state weighting, you do not diverge too much from the behavior policy. Okay, and so there's a lot of different algorithms fit into this framing, and with the main questions being kind of, how do I pick the state relevance weights? How do I pick the divergences? And how do I pick the radius? Okay, and usually the radius is a tuning parameter and the divergence is some version of a KL divergence. Okay. Now, that kind of Bayes rule-like update that I showed you, my paper is going to prove that that is the exact solution to a trust region optimization problem with particular choices for those elements. Okay, so particularly it's kind of a lot to digest, but the occupancy measure, sorry, the occupancy under successful trajectories that actually succeed is what forms the state weighting. A chi-squared divergence instead of the usual KL is what forms the geometry of kind of the balls in this space. And the radius is not a tuning parameter. It is determined automatically by some feature of the behavior policy and the data. And what you can kind of see here is it's determined by action. So we can spend more time on this later. If I were you, it would be hard to digest all the math kind of quickly. But hopefully the high level of this looks like a trust region optimization problem, not one you've exactly seen before, but one where you need to be really an expert in this space to appreciate why it's different, except for the main qualitative feature that the radius is determined automatically, not set by you. Yeah.
Could you just remind the action draw influence if we expect it to be higher in states in which the behavioral policy it's more stochastic or less stochastic? So in which states you allow more movement from the behavioral policy?
Got it. In general, exploration is helpful in allowing you to move more.
Okay.
So I'll flag that later. It sort of is, the action influence is determined by two things. One is sort of how diverse the actions are under the behavior policy. and the other has to do with the extent to which your actions themselves are highly determinative of success versus it taking kind of either luck or a long string of actions that are, happen to land.
Or via the Q value, right? And I remember now. Okay, yes. Thank you.
Yeah. Okay. So this slide is also kind of here. At least for me, I need to spend time kind of with the paper to grasp this sort of thing. That's also to kind of flag that one of the things you can unpack kind of as an expert in this space is, okay, how is this different from other policy optimization procedures that I'm familiar with? The superficial difference is definitely that we didn't explicitly solve any policy optimization problem. We just imitated successes. Okay. Now, what that is implicitly implementing uses a different geometry, this chi-squared geometry instead of a KL geometry. What does that imply? Well, if you spend time with this is an exploitation-friendly kind of structure, one that enables you to increase the probability of actions you were previously playing, but not an exploration-friendly one. So it's very, very hard to explore actions that you almost never played under the behavior policy, under this constraint. Okay, so there's some math kind of in the paper that relative to this version of KL, it's much harder to play an action under this constraint that was rare under the behavior policy. Yeah, David.
Yeah, could you just explain a tiny bit the link to sort of exploration exploitation? Because we're talking about an optimization problem rather than an interaction, so I don't immediately see the connection.
Got it. Yeah, the whole policy optimization literature can get a little confusing around this because it often mentions exploration, but it not really in a learning sense. I think that language is loose. Let me instead say precisely the behavior policy is may play certain actions very infrequently at certain states. Now, when you have a trust region, it says don't deviate too much from the behavior policy. And the question is, if you played an action rarely under the behavior policy, does the new policy have to play that rarely? And how rarely must it play? Right? And there's some trust regions in literature that allow you to play actions that were previously rare quite a bit. And in that sense, they allow exploration. They allow to move to actions that were not so common under the previous data. Their constraint instead is more that they can't write off things they were previously doing. The constraint under chi-squared here is the reverse. It can do things it was doing previously even more. It can kind of sharpen in on one way of behaving, but it cannot, something that was very rare previously, it basically can't do it now.
Perfect, thank you.
Yeah. So I mean, one takeaway for me is that I would not expect this kind of optimization procedure to discover totally new ways of acting. We're not covered before. Yeah, Amit?
Hey, I might be jumping ahead a little bit, but towards the end, you said something like you might be sharpening a distribution, but you also said earlier that because of this chi-square sort of divergence, you don't really move too far away from the base model. And I was just wondering, in practice, on the empirical side, what people see is reward hacking and just mode collapse. Isn't that decisively moving towards a particular direction rather than moving too little? I don't know if my question is clear.
Yeah. So it is possible. It kind of depends on the action influence and kind of the radius here. It is possible for this trust region to allow you to move quite decisively to behaviors that were reflected under to a subset of behaviors that were reflected under the data generating policy, the behavior policy. So it's possible to sharpen quite a bit, technically, in some cases, under this theory and in practice. It depends. So that could happen due to training issues where you fit a policy that was not your target. You tried to imitate this thing, but you didn't. That's one reason you could sharpen. The other reason you could sharpen has to do with kind of the right-hand side being permissive.
Got it. Thanks.
So, yeah. Okay. Yeah. So in some ways, my language here, though, is informal in this sense. I'm framing success conditioning as a conservative policy improvement operator, and that it's maximizing policy improvement without venturing too far outside of observed behavior. Okay, but what is too far is, I guess, a question. Okay, so but I still think as sort of a high level thing, you can kind of unpack the details of what this particular trust region means, and I think there's a lot of room there to see whether that's explaining things we see in practice. But just at the highest level, it demystifies for me a little bit what this procedure is doing. It's saying, okay, there's no explicit decision-making objective, but I liked it that we were just doing the same kind of training as pre-training. I'm saying, okay, actually, this is policy optimization, kind of as I know. Okay. Now, sort of that's one main result. It's interpreting this as a policy improvement operator. The second result that I call kind of a main result in the paper, which is describing how much a single iteration of the success conditioning operator improves your policy. Okay. And it turns out that if you inspect kind of this trust region formulation and you see exactly what optimizes it, you get the following kind of a triple identity. One term is the extent to which the new policy you get out of the update improves upon the behavior policy you started with in terms of the thing you care about, like expected reward in the future. Second term is a measure of how much the policy itself changed. Okay, in the sense of its action probabilities deviating from those of the base policy under this chi-squared measure. Okay. And the third term is a feature of the environment and base policy, which determines basically whether this operator is going to be successful in this environment. Okay. So what are some consequences that you can kind of see if you just looked at this identity and spent some time with it? Okay. One consequence kind of at a high level is that bandit example of a failure mode that I showed you, that is the failure mode of success condition. Okay. Why? Well, basically what happened in that problem was that action influence was small. The influence of whether you picked action 1 or action 2 on the final probability of success didn't matter much. Mostly success was determined by a coin flip. Okay. And as a result, what we saw manifest in that example is exactly what this theory says happens in general. The policy itself barely changed, and it barely improved. Nothing got worse, but you didn't see change really at all by applying this update. Okay. Now, by the identity, that's kind of the only failure mode. If you don't get large improvement, so notice the right-hand side is non-negative. Okay. So if you don't get large improvement, the only thing that could have happened is that the action influence is small and the policy doesn't change. Okay. Now we already talked about this a little bit in answer to one of the questions. This kind of, if you want to see when does this occur, it basically can occur for two reasons. So you could have low action influence because the behavior policy, basically the randomness in the behavior policy does not greatly impact final outcomes. Okay, that's kind of what it means to have low action influence. And that could happen either because the policy is nearly deterministic, in which case, well, clearly randomness doesn't have much impact. Or it could happen because actions themselves do not result in substantially different success probabilities, which is more like a feature of the environment. Okay. And then action influence is also. Okay. A second kind of consequence of this identity, which with more bandwidth, I'd really like to spend time doing empirical work around this, is that it suggests a diagnostic. Okay, so if you put yourself in the mindset of somebody doing offline reinforcement learning, where you can train a policy, but deploying it to get new trajectories and getting labels for whether those trajectories are successful is very expensive. Put yourself in that mindset. Okay. Now, a problem with success conditioning is that you train this new policy, but it doesn't give you a value function. It doesn't give you anything like that that would indicate whether you expect the new policy to be better. It just gives you a way to a new prescription for actions. Okay. But out of this theory, it suggests a kind of proxy for how much improvement you'd get that you do see before deployment, and that is the extent to which the updated policy diverges from the old one. Okay, because if the updated policy diverges from the old one, then that ought to indicate that you have large improvement. Okay. Now, whether this actually works for the current like training pipelines that are popular that approximate these objects, I really don't know, and I'd love to go check that out. Okay, but there's some potential. Okay. Now, I think what I'll do is kind of go through these connections and then just go through the last part, which is connections to policy gradient. And then I'll flag some extensions and not go through them and save the time for questions. Okay. So sort of a last thing here. I was sort of going one direction. I was saying, okay, let's start with success conditioning and prove that if you did this particular procedure, that it would look in disguise kind of like things that are familiar to us. Now, something else I'd like to think about is, can we see more mechanistically a point at which this becomes almost the same procedure as something like reinforce? Okay. And ultimately, I think you can. My claim is that you can understand reinforce in this binary reward setup as being really within the success conditioning family as well. It's a method for imitating successes. Okay. So here's kind of the claim, made a bit more formal. Okay. Let me write down the success imitation loss. Okay. So there's two forms of policies in this loss. There's the pi naught policy, the behavior policy that is generating the data. And then there's the policy we're trying to train, pi. And the loss is asking, under trajectories that are successful, under actions taken from the behavior policy. So basically you simulate the behavior policy and you keep the trajectories that succeed. Under those, does pi predict the actions that were taken? Makes sense? So when I started, I said that the way people implement success conditioning is by minimizing this loss. Okay. So let's write that. You could think of iteratively doing success conditioning. You generate trajectories under the base policy. You keep the ones that worked out. Then you update the base policy by training a new policy that minimizes this loss function through many gradient steps. Then you go again. Okay. So you train to the minimizer. Okay. So a natural question then is, what if I didn't train all the way to the minimizer? Right? What if I just took a few gradient steps and then I gathered new data? Okay. And my claim is, if you took just one gradient step on this loss function and then updated the policy that generates data, then you would be doing reinforce. Okay, in a literal mathematical sense. Okay, so, and reinforce is usually not written as minimizing this loss, but it's the same. Okay, through a short calculation, it's the same. Okay, so I kind of have that here. Okay, so how do we interpret this then? One view, which I think is kind of wrong, is to say success conditioning is then just reinforce. I don't think that's right. I would instead think of reinforce as like a very special case of success conditioning where you are very incremental in your updates. Okay, so here's why. So the reinforce has in its framing every step has to be a gradient. Okay, a gradient of the reward function. And here the gradient of the only step in this procedure where you would get a gradient of the true reward function is if pi stays exactly at the data generating distribution. So reinforce by its construction is only faithful if you are completely on policy. Makes sense. Whereas the thing on the left moves way off policy because it freezes the data generating distribution and it keeps training pi to maybe diverge further and further. Okay. And what I sort of like about the thing on the left is it frees us from thinking of everything as being a policy gradient at all times. And instead, it fits into this framework where you are you maybe generate a large batch of data. You do many gradient steps to improve things. All right, and then you generate a large batch of data again. Okay. All right. So I won't go through these, but just if you spend time with the paper itself, stuff that's in there that might kind of be on your mind. One is sort of, what if there's some estimation error? I think this part could probably be tightened, but I have the kind of requisite section in there that puts in the epsilons, right? That if you did success conditioning from data and you got a near minimizer of the loss function it's trained on, but not an exact one, does it still give you a policy improvement? Okay. And the other thing we could talk about offline, if it's of interest, is kind of what happens if the reward is not binary, and the different ways people deal with that. Okay. And so there's kind of one substantial section in the paper which is about thinking that through. Okay. All right. So kind of closed here, we've formalized some methods that are discussed disparately and called them success conditioning. We've then formally interpreted that operator as a kind of policy improvement update and coined this term action influence, which seems to be governing when success conditioning leads to rapid improvement or slow improvement. And given the connections to reinforce that I detailed at the end, I suspect that action influence is kind of there lurking, governing a lot of whether post-training is rapidly improving or not. Okay. And I'll close here and take kind of questions offline. Thank you all for staying.
Thank you. Great talk. Okay, we already have a question. Feel free to go. Or maybe it was a clapping. Okay, Sutek, go ahead if you want.
Hi. So am I audible?
Yes.
Yes.
Yeah. So my question was that could you go back to the slide where you framed success conditioning as the constraint policy optimization problem?
Yeah, I did in a couple. The mathy slide, the one that looks like.
Yeah. So where you framed the optimization problem, I guess, in the
This one.
Yeah, this one. So here, as I can see, the radius, the RHS of the constraint, that's kind of fixed. That's determined by your base policy and data. So I was wondering, and the optimizer of this problem is your success condition policy. I was wondering that if we want to control the RHS somehow, if we want to, like, suppose increase our trust region, then is it so determining if that is variable, say for example the RHS, then could we maybe get some others, like is that possible to write that as a, say, a function of the success condition policy and say also the failure condition policy, and maybe the radius determines how close it is to the success condition policy and how much the failure condition policy also plays a role in that. I'm not sure. My question was pretty vague, I guess, but I'm just saying if the radius is controllable and if success and failure condition policies would play a role in that. Thank you.
Yeah. So let me also translate one step of this, because I think you made one. You had one insight there that might not be clear to everyone. In other versions of trust region problems, there's a tunable radius. And one reason, though, that it's easier to kind of tune that radius is that those methods kind of are explicitly framed as optimizing a particular objective. Right? They estimate value functions, they kind of move in that space. So they would actually estimate this L, and they estimate the movement and so on. So here, because all you were doing is imitating a particular actions along a particular subset of trajectories, it's a little less obvious how to make the radius tunable. But I guess your proposal is something I did think some about, which is you do potentially have both the base policy and the success conditioned policy, and you could think about methods of amplification where you try to kind of move along the line between these two, or move along a curve between these two, but either stop shorter or amplify further, kind of extrapolate further along this curve. I think I thought about this. I can't remember the final result. I think one challenge is for stuff to work out very cleanly, you might need to amplify more at some states than at others. That starts to get a little messy. But I do think this is a promising direction that I haven't fully explored.
Thanks for the explanation. Yeah, that's exactly what I was asking.
Any other question? Okay, go ahead.
Hi, thanks for the great talk. So when I was reading upon these kind of like a policy improvement stuff, I've seen people interpreting this as a EM algorithm, like where you have like the success condition sampling is the sampling stage, and then you have an improvement stage. And if you take a probabilistic interpretation of the RL, like back in the days where the reward that you observe at the end is the end goal, and the trajectory in the middle is treated as a hidden variable, latent variable. Basically you can view this as solving that latent variable model for the posterior. So I was wondering how this framework kind of fits in with that Bayesian interpretation of the RL.
Yeah, I mean, the truth is it's tricky. You know, at the highest level, say you look at like RL as inference, that framing, at the highest level, it definitely dances around all the same ideas. So it kind of starts with this framing, dances around the same ideas, but then concretely starts putting in certain approximations. And concretely, it does end up with different operators. Like all these things tend to be KLs, or exponential weightings of different kinds. So concretely, it's like not exactly the same, which is something I can superficially get at. But I wonder if there's a clean way to make them all look the same. And I haven't really figured that out. But I think you're right that there's some kind of EM interpretation also lurking here, and maybe that also might be another framing, you know, of this stuff too. Yeah,
I guess a question from me. To what extent is throwing away essentially negative data a good idea? So like, it's if you gave me a classification task and just gave me the positive classes, and my task is to figure out which area is the positive area so that I can be or stay there, I would also want to see the negative examples. Here it seems that we're okay with throwing away the negative data. Statistically, are we losing anything? Do you think this is a good idea?
Yeah, instinctively it feels bad. That's my gut reaction at first too. You know, I can't really tell. I think that one reason to think that it's maybe not such a huge deal is, yeah, I can't tell if it's really more than something like a factor of 2. That somehow, I guess let me tell you something that is my first instinct, but then I usually decide is wrong. My first instinct is, what if you almost always fail? Right? So this feels like the worst case, because what if you almost always fail? Then you're throwing away basically all your data. But if you almost always fail, then actually you were getting almost no signal from the failures. The signal is really coming from the successes. So that's one way to dance around it.
I was going for exactly the opposite as being the worst case. So I would be worried, but there's one absolutely atrocious sort of set of actions. And if you don't learn that that set of actions is there, if you never receive a negative signal, I guess you're learning to imitate. So you learn not to perform actions that are not in the policy. You might just not do it as sharply as you would have done. But with this chi-squared stuff you've been talking about, and with how much it downweighs actions that are rare, maybe it's already fixing that problem.
Right. I mean, I think that the filtering would hard remove all of that from the data. But whether the training in practice is going to write it off, I can't. Yeah, I can't.
Yeah, maybe a slightly more technical question. So in one of the extensions, you said you might want to extend this to general rewards.
Yeah.
But I feel like most of what you presented seems a bit specific to binary rewards, no? Like, for instance, what about your triple identity? Does it still carry over if you have general rewards?
Okay. So, got it. Okay, so there's I'll kind of give a little more detail on what that section of the paper does. Okay, so there's a way, here's sort of the punchline at the highest level. There is a way to reduce a general reward problem, like a bounded reward problem, to a binary reward problem.
Okay.
And then all the theory carries over. The operator carries over, the movement identity carries over. The crux, though, is that is not what people do in practice. That reduction is not what people do.
Okay. Okay, I see.
So I'll kind of flag kind of what the two cases are. So I'll kind of do it in math. What would you do as a faithful reduction? Well, let's say you got a reward of 0.7. Rewards are normalized, so they're in 0, 1. You got a reward of 0.7. Well, you could just kind of treat that as a weight. There's as if it's like there's a further randomization step where you round to 1 with probability 0.7, round to 0 with probability 0.3. And there's maybe more data efficient ways to do this, but that yields the same objective as maximizing expected reward, some kind of reduction.
Oh, yeah, okay. Yeah.
But what people have done in empirical practice is instead they pick a threshold. And they say, okay, success is if your reward is above 0.8. And so one part of the paper tries to understand if you train by varying this threshold, but you actually care about dense rewards, what does that do?
Okay. I see. Yeah, thanks.
So I have one worry about the procedure you described, in that it's going to suffice for getting the sort of right first order behavior. It will get the average right, but this sort of generalization should destroy all the variance information. So you won't get the sort of fast rates you might associate with bounded targets. Do you reckon there might be a better procedure? Oh, let's put it this way. Yeah, do you think there's a way that doesn't penalize, but directly deals with dense rewards and gets sort of second order type rates rather than just?
Yeah. So I'm not sure I'm proposing this, to be clear.
I see.
This is more what is being done, but this is kind of a baseline of what, it's not faithful anymore. So, but you're right, even if you were to go this route, there's something a little better than randomizing. So stage 2, I'll go in 2 stages. Stage 2, clearly the same as this, but a little less dumb, is you could randomize many, many times. So you could take a trajectory, copy it over and over again, and randomize independently for each one, so that you kill that variance. But you suffer a compute penalty as you do that. Now, but once you look at it, the copying many times and relabeling many times, you can just kind of write down what the loss is. It's a reweighted loss. So you can shortcut the process. That's a good question.
Yeah, thanks for the great talk. I have a more sort of conceptual question, maybe, and maybe it doesn't make sense because it just struck me. But so I was wondering, like in GRPO, for example, they also have a variance like quantity, right, in the denominator. So if you have like a larger variance, then basically you have a larger spread. Then you have a smaller advantage for a prompt, and you make a smaller move. Whereas under your theory, from what I understand, if you have a larger spread, you want to make a larger move. Is that a correct interpretation?
So I'm not positive, but I think that GRPO, the way it's implemented, has something a little different going on that is shared with these other recent papers. So maximum likelihood reinforcement learning paper, and this other one by Ian Osband on delightful policy gradients. They all share this idea that you want to amplify kind of rare actions that led to rare successes. Like, so for instance, in the prompting case, you would want to amplify hard prompts, right? Because right now, all of your data is coming from these easy prompts if you just condition on success. So you'd want to reweight. And there's some of that going on, I think, in GRPO. And I don't know how much of it carries over to general problems. So one kind of gap in the way I've formulated things very generally is there's no notion of kind of like prompt answer. And so you can't do that kind of reweighting. If that makes sense.
Right.
So I think there's a lot of, but one thing I like about the imitation learning perspective is it frees you very clearly to think like, okay, I'm gonna tweak the imitation distribution. Like I'd rather emphasize harder prompts or so on.
Got it. Thanks.
Perhaps I can stop the recording if someone wants to ask offline.